and set up your page. If you need to pause this, remember pause this whenever you need to. And we're on our 7th page of notes for this unit. So make sure you have them all. If I messed up on a page, send me a note and I'll fix that one. I think B9C, no, B9B, I think the second part I forgot to put the link on, so I'll fix that. Alright, so we're doing B9C. And B9C is really a nice, short, sweet TEK. We just have to kind of split it into a couple of pieces, so it's not going to be too long here. It says basically identify and investigate the role of enzymes. So identify and investigate, which means that's a lab. If you guys were here in person, you would get to do a lab. Identify and investigate the role of enzymes. So our next lab, will be dealing with enzymes. You are going to deal with the enzyme pectic enzyme, or pectinase. If it ends in ASE, it's an enzyme that breaks something down. So enzymes can help reactions happen, whether that reaction is a reaction breaking something down or putting something together. They speed up those chemical reactions. Alright, so again, that first piece here, and we've talked about this several times in the notes, so I'm going to put a little box here. It's not one of the big 4 organic compounds. It is a type of one of the 4. So enzymes are proteins. We've already talked about proteins. So if I take my notes and I flip back a couple of pages to proteins, enzymes should be on there. And sure enough, I have protein here, and if I flip it on down, right down here, there it's talking about enzymes, right here. So we've talked about enzymes before. We're just going to get a little bit more in detail with them. So enzymes are proteins that are biological catalysts. Okay, biological catalysts, and I'm going to add a little piece here because this is the way you'll see it phrased on the test, which is, I find it kind of irritating that they did this, but you know, again, they don't ask me. In biochemical pathways. Okay, so 2 things I want to point out about this. One, again, catalysts. This is the probably 2nd or 3rd time I've written down like this. Catalysts are chemicals that speed up chemical reactions but aren't used up in the process. So they speed up the chemical reactions and are not used up. They're not a reactant, they're not a product at all. So I'm going to give you an example of a catalyst. It's not an enzyme, but it is a catalyst, and it's one that you'll use in chemistry next year when you deal with this. So I'm going to write this reaction down. Do you guys remember H2O2? What is that? Hydrogen peroxide. Okay, hydrogen peroxide is a really unstable compound. That's why they sell it to you at Walmart in a brown bottle, because even light from the room will cause it to break down faster. Normally, it just breaks down. I'm going to make a long arrow. You guys make a long arrow too. It breaks down into water and oxygen. And I'm not going to worry about balancing the equation. I'm just going to leave it as is right here. If you shine light on it, it'll make it go faster. Usually it's not going to... You can see, if you watch it, you can see little bitty tiny bubbles in it, the oxygen bubbles coming up, but it's not that fast. But if you want it to go really fast, what you're going to do is you're going to use a catalyst. And when you talk about there being a catalyst, usually it's written on top of the arrow. So in this case, the catalyst is manganese dioxide, MnO2. Manganese dioxide. This manganese, it's not a reactant, it's not a product. We stick it in there and it's still all there at the end of it. So if I take a test tube full of hydrogen peroxide, I dump this little manganese dioxide in there, it looks like, again, black baby powder. All of a sudden it'll fizz up. All this reaction will happen really fast. Like within about 10 seconds it's over. And so it'll all fizz up in there, maybe even shorter than 10 seconds, and we'll have all this oxygen there that's being produced and then water. So this is an example of a catalyst. It's not an enzyme. Enzymes are specifically proteins. So this is like, 3 atoms, Mn and 2 O's, right? manganese and 2 oxygen atoms. There's 3 atoms total. It's a dinky little thing. When we talk about enzymes, they are massively huge. They could be 10,000 atoms. Just depends on what the enzyme is. They're just big, big, big Godzilla things. So they're not as easily used, like outside of a test tube, not as easy to grip them, not as easy to use them, and so on. Now, the other thing I want to point out is this biochemical pathway. So I'm going to underline this piece right here, and I'm going to put a little arrow down to this one. Biochemical pathways. This is the phrase I used because that's what they used on the STAR test. So I want you to be aware. It's just it's just a matter of the phrasing. How do they say this? Sometimes the way they say things throws us off, and so we have to look at explaining things in a lot of different ways here, with a lot of different words here. This biochemical pathway, or pathways, they're series of chemical reactions in organisms. So if you have one pathway, it's a series of reactions in organisms, because it says bio, right? Life. So it's in organisms. And these you should know already. Respiration, cellular respiration. So here's some examples. Cellular respiration, photosynthesis. And when we talk about those two, you could say photosynthesis, and it has a whole bunch of biochemical pathways in it. So there are lots of little sections to it. Same with cellular respiration. There are lots of little sections to it that are going on in here. But when you have a reaction, and in reality it's got a whole bunch of steps to it, that's what they call a biochemical pathway. Fermentation, we briefly talked about fermentation. When we talked about cellular respiration, one of the ways that if we run out of oxygen, we can go through a different pathway and we form lactic acid in our muscles, and it kind of hurts after you're running a while. You just stop and breathe and it goes away. In plants, they don't do that. Instead of doing lactic acid, they actually make alcohol when they don't have enough oxygen. So it's called fermentation here. And the other one I'm going to put on here is glycolysis. Not that you have to know what it is, but just that you can be familiar with it. It's a step within the cellular respiration, glycolysis is. Okay, so we have enzymes. They're biological catalysts here. And here's an example of just a generic, this is just a catalyst, not an enzyme. And I'll give you an example of an enzyme in just a little bit here. So we're going to talk about the structure and function again. So the structure, most enzymes are proteins. So what are they made of? Yep. And the instructions for making them are in your DNA. So again, chemicals that your body makes, that's all the instructions for making these things are in your DNA. Someone asked me earlier, when we talked about enzymes, well, can something be in your body that messes up how the enzyme works? Well, yeah, there are lots of things that do. Different types of poisons can actually kind of mess up how the enzymes work, and so I'll mention that again a little bit later here. So most of these are going to be proteins, and they're folded in a very specific way so that only one reaction, one enzyme, one reaction, that's it. So when I say folded, remember there's big Godzilla molecules. Proteins naturally fold in on themselves. They wad up, and the way they fold makes a certain shape. Which elements are sticking on the outside, which atoms are on the outside, which combinations are on the outside, those are the ones that are going to kind of determine what it does here. So they're folded in a specific way. This is the structure. If you mess up the making of this protein, like there's a mutation in the DNA and it messes up the instructions on making the protein, it'll cause it to be folded differently and it won't work right. So they're going to be folded in a specific way so that one enzyme only works for one chemical reaction. So one enzyme works for only one reaction. How to say type of reaction. And I'm kind of mangling that there a little bit. So this enzyme can be used over and over and over again, but it only does with one set of chemicals. That's it. It's kind of like when I have a key. I can use this key to get in the room over and over and over again. But even though these two keys are really similar, made by the same company and everything, they're really similar, this key I can't use to open my room. It's just slightly different enough that it's not going to work. The little grooves and protrusions in here are just slightly different, so it's not going to work on my door. This one, it's only going to work on this one door, and that's it. Yeah? That's kind of like the enzyme. It's only going to work on that one chemical reaction. It can do multiple of those reactions, like the same reaction it can do, 15, 20 times, but it's only that one kind of reaction, just like my key only opens that one door there. Right? Yes? Okay. Now, this is really important right here. One enzyme, one reaction. On the function, and as I said, the function is really closely related to the structure. So the function is heavily dependent on the structure. So the rest of the stuff that's on the paper is going to be about the function here. I'm going to give you a little piece of information that is not going to be on your test, but it's really important. So what I want you to do is I want you to pick a different color. If you're working with pencil, get a pen. If you don't have any colors, go and get one. You are young, you're healthy, most of you are athletes. Walk halfway across the room and get a pen or something or other. But pick up a different color. And I'm going to talk to you just really briefly about something called collision theory. It's one of those theories that's really simple and straightforward, and once you hear it, it's like, duh, that makes sense. So collision theory. Collision theory is how they try to explain chemical reactions happening. So collision theory says that for any chemical reaction to happen, the chemicals have to hit each other with enough energy. They have to collide, right? Hit each other. The reactants, yeah? The chemicals have to hit each other with enough energy to activate or start the reaction. And the word activate is usually what we talk about. And what that means is, and we just finished studying over this in AP Chem, so they have to hit each other with enough energy so that they overcome this thing called an activation energy barrier. So they have to hit each other, collide with each other hard enough. One way you can speed up chemicals, can't you just heat them up? If you heat things up, don't they speed up? Like if the molecules, they're moving slowly if they're cold, and then when you heat them up, they move faster and faster. Like if this is a solid, they move faster and faster and faster until they break apart, and then they start sliding around each other. So they change from a solid to a liquid. Yeah. So they have to hit each other with enough energy to activate or start the reaction, and they have to hit in the correct orientation. Okay, and I'm going to show you a little drawing really quickly here. So let's say I have a chemical reaction. I'm going to do a really straightforward one that's pretty common in chemistry. So I'm going to cover this up just a second and I'll undo it. So I'm going to do sodium hydroxide plus hydrochloric acid. Okay? And this is a cool reaction. It's called a double replacement reaction. Focus. These first two pieces of the chemicals are going to swap places. So on the other side of the arrow, I'm going to get the sodium hooking up with chlorine, and I'm going to get the H hooking up with the OH. Okay, what's that? Isn't it the salt? That's sodium chloride, stuff you put on your fries, right? I got two H's and one O. What would that be? Yeah, did you guys see that? Two H's, one O. I just wrote it differently. I can write it like this, can't I? Yes? Okay, so we have water here. So let's say here's the sodium, and here's, it's called a hydroxide molecule. This one's negative, this one's positive. So here's my sodium ion, here's my hydroxide ion. And then my hydrogen chloride gas, or my hydrochloric acid, I have, here's this one, and here's the chloride, sorry, that's a plus sign, and there's my chloride ion. if these two hit with each other, first of all, if they just barely bump each other, there's not enough energy to do anything. If they hit each other hard enough, nothing's going to happen if they're arranged this way, because here I have a positive and a positive hitting each other, and a negative and a negative. Really? What am I doing here? Let's fix this really fast so it actually makes sense to what I'm saying. This one's negative. So I have the negative and negative hitting each other, and positive, positive. Do they attract or repel? Yeah, so there's no reaction happening. In order for this to happen, I would have to have, here's my positive sodium and my negative hydroxide ion. And then here is my negative chloride ion and my positive hydrogen ion. Now when they hit, the negative hits the positive and the negative hits the positive here. Now if they hit hard enough, they can have a reaction because they're oriented correctly. So two things, they got to hit hard enough so it actually does something, and two, they have to hit in the right orientation. These are little bitty dinky molecules. I mean, sheesh, 3 atoms, and that's it. So they're tiny. When we talk about enzymes, these are just gargantuan molecules. Still so tiny we can't see them through the microscope, but in the world of molecules and atoms, they're massive size. They're like dinosaurs, right? So they're huge. So it's much more difficult to get these huge molecules in line with each other and oriented right. And that's the job of the enzymes. The number one thing they do is they really get them oriented right. So pick up your original color. I want you to circle 2 things. So these enzymes, make sure that they get the chemicals in the correct orientation. That's the most important thing, and allows them to hit with enough energy to activate the reaction. Not all reactions need an enzyme. Like this paper, I can get it to chemically react with the air. As it sits right here, my paper is not chemically reacted with the air. But if I give it enough energy to start the reaction, it will. And I can give it enough energy if I get a match out and I light it, I can heat that paper up to 451 degrees, right? Yeah, you guys get that? Did you read that book? Yeah, 451 degrees. I can put the match to it, and do I have to hold the match to it to keep it going? No. Once I give it enough energy, I take the energy away that I gave it, and it goes on its own. I don't have to add any more energy to it. It's going to go on its own. But I had to get that original energy there to kick it up enough to start the reaction, right? Okay. So, going back here, let's look at the enzymes. The enzymes speed up chemical reactions by doing 2 things. Okay, the first thing is that they lower the activation energy. How much energy does it take to get these reactions going? Okay, so again, the activation energy. How do we get it activated? How do we get it started? The second thing, the number one way they do this, by lowering the activation energy, the number one way they do that is by orienting the chemicals correctly in space so that they can react. Think of it as a 3D kind of thing. That's the key to what they're doing. Now, how do they do that? You're going to make a little sketch. Okay, so here's what we've got going on here. So I'm going to make a little sketch. I'm going to come up here. I'm going to make something that looks like this. So it started on the same line and ended, right? Can you make something like that? Draw that. I'm not a very good artist, so I'm going to draw something simple that I think all of you guys can draw. Then I'm going to bring it down here, and I'm going to make a triangle. Yeah? I'm going to connect it over here, and I'm going to make a square. You got that? And then I'm going to connect it back up. So there's my enzyme. So this is my enzyme. Okay, keep this color out and get another color. Get your other color again. Or a different one. So here's chemical number 1, and it's going to fit right in there. There's going to be a section of it, or maybe even the whole thing is going to fit right in there. So this is a substrate. It's called a substrate. So this is substrate number 1. And then there's going to be another chemical that it's going to chemically react with that fits over here. Looks a little bit like a mutated Texas. This is substrate number 2. And right in here is where they're going to chemically bond with each other. But the enzyme, you see that the enzyme got them oriented in the right direction so that now they can bond with each other. And once they're in the right direction, oriented with each other, it takes a lot less energy because a lot of times the energy is used up because they're bumping around, not getting in the right direction with each other. So here's substrate 1, here's substrate 2, here's where they're going to chemically react, here's our enzyme. And these are called active sites. So here's an active site. They've got, one's an A and one's a P. We don't even care. Active site. So these are the active sites for that enzyme. And you're going to have 2 chemicals fit in there. Notice these are the only chemicals that are going to fit in there. Now these are chemicals that are made inside the body. So you're the organism that created these chemicals. There are some chemicals, let's say you're some poisons. Somebody got bitten by some strange snake or whether and injected a poison. Sometimes there are poisons that can actually bind to the active site and they inhibit. It's like the wrong chemical gets in there and they inhibit the whole thing from happening. So they're called inhibitors, obviously. But you can get chemicals in there that can stop this from happening. They're not chemicals that your own body makes though, right? That wouldn't make sense to do that, would it? Yeah. So they're going to have that here. So the chemicals react together to form a new substance. Then they're released, or it. The enzyme can be used again. Oh, I'm running out of space here. And it can be reused over and over and over again. Some enzymes your body has to continually make. Some enzymes your body can just make some of, and then it relies on those for a long time. Amylase. Do you remember the cracker? You stick the cracker in your mouth. It's a complex carbohydrate. It doesn't taste sweet, but you keep it in your mouth long enough, and that spit that has amylase in it starts working on it. Starts to taste sweet. Once you've written this down, flip over to page 33 in your notes really quickly, really fast. How much time do I have left? Is this 7th? Okay, so I have a little bit of time. All right, page, I think it's 33. Yeah. Okay, so I'm going to shrink my stuff down here a little bit. If you look at page 33, what happens is we have this picture of this enzyme going on here. I'm going to run this backwards on the page, so that we're going to be looking and going from right to left on here. So let's say this enzyme is that amylase. Amylase. You notice the enzyme has a weird shape to it, right? Do you see how this piece right here fits up in there? This would be a starch. That's our substrate. In this case, if we're talking about the amylase, there's our starch substrate. We're going to break that down. So the starch fits up into the amylase, the chemical that's in your spit, and so it looks like this. This is an active complex. Okay, so here's our amylase enzyme. Here's our substrate. Starch was what we're using for this. And then look what happens. The starch breaks down into a simple sugar. And here's another simple sugar. And how does that taste to you? Sweet. And this is our enzyme, amylase, that can be reused. See, it's just like what it started out as. It can be reused now. That's how enzymes work. They set it up so it fits right. So when this is a decomposition reaction, so it's a little bit different than what we do when we put stuff together. But basically, we have the same thing going on here, just in reverse in many cases. Once you've written that down, go ahead and pack it up.